Okay, good morning everyone. Let's get started. Good turnout for 9 a.m. on a Friday morning. Well done. Okay, so what we're going to do in today's lecture, in yesterday's lecture we looked at the principles behind evaluating surface, behind being able to do surface integrals, whether in vector, scalar, non-parametric or parametric form. And what we're going to do in today's lecture is we are mostly just going to go through a number of examples on how to do surface integrals. So that's a little bit of a grind, but a significant number of the most difficult questions that you're going to encounter usually on the exam paper for this course are complex surface, by which I mean complicated surface integrals. So it's good experience to go through some of these. All right, so we'll start off with the slightly simpler flavour of surface integrals, which is when you have a scalar surface integral, and we'll consider first the non-parametric case. So yesterday when we were talking about surface integrals, we were imagining our 3D space, x, y, z, and we have some surface in this space, and quite a lot of what we were talking about were vector surface integrals, where you needed to work out what was the normal to the surface at some given point, and you're going to do a dot product of that with the vector field to give you a scalar, which you then evaluate over the surface. And we talked about the various tricks and methods by which you can do this, the most common of which is to project your surface down onto one of the two-dimensional planes with a correction factor and evaluate it there. In terms for the scalar surface integrals, it's a little bit easier. So instead of having some vector field, which you need to dot product with the normal of the surface to work out a scalar, in a scalar surface integral, you already have the value of the integral. You have a scalar at every point on your surface. So all you are doing when you have a scalar surface integral, in particular in the non-parametric case, is you are given some integral, which is described by S in the question. Again, that's always, and I'm repetitive on this point, but that's always the tricky bit, is to work out the words that describe S, what they mean, and turn them into actual ranges and shapes. So you have some scalar as a function of position evaluated over your surface. And what that becomes then is that becomes a surface integral projected onto some axis. So typically this would be the xy plane, but there's no reason why it should be. This could be any of the three possible planes. So you project your surface onto the plane. Your function, in the case that you're projecting down onto the xy plane, then becomes xy and some g of x and y, okay, which is the function which is describing the height of your surface about as a function of x and y. So z is just some function of x and y. Times by the projection factor, which we discussed yesterday, which was the 1 plus dg dx squared plus dg dy squared term. So this is not very well presented. This is in series, it's not being divided by it. And then times by our dA, and our dA is usually, if I'm projecting down onto the x and y plane, dx dy. So what you'll find is that when you're evaluating these surface integrals, you always only have one complicated term on the right-hand side. So in the case of the scalar surface integrals, your complicated term is your projection factor. In the case of the vector surface integrals, as we'll see shortly, your complicated term is your normal to the surface, which you have to dot product with your vector field, because in the case of the vector surface integrals, this projection term, this area term, cancels out, as we discussed yesterday, with the normalization of your normal. Okay. Right. So this is the case of doing a surface integral of a scalar field where I have some surface which is essentially described by some function which is a function of x and y. The other type of surface integral then, and of course these two types of surface integrals, they also apply to the vector surface integral. So you end up with a matrix of 4 different types. In this case, then, you have some surface which is described by some parameters r of u and v. And you'll remember that is equivalent to a position vector for the surface, which is equivalent to some x of u and v in the I direction, plus some y, which is a function of u and v in the j direction, plus some z, which is a function of u and v in the k direction. So that's our parameterized surface. And in this case, then, it's the same. We have our function as a position, as a function of position. So we have the value of our scalar, which is a function of position, which in the parameterized case is given by r of u and v, multiplied by our projection factor, which you'll recall from yesterday, is the value, is the magnitude of the cross product of 2 perpendicular vectors in the surface at that point, which is given by dr du cross dr dv. And in this case, then, you would integrate that with respect to du dv. The only difference between these, then, and our vector surface integrals is that our scalar here, in the case of the vector surface integrals, is the dot product of our normal and our vector field, which we're evaluating through that surface. Okay. So let's jump straight into an example. So let's evaluate the scalar, let's do a scalar surface integral on a non-parameterized surface. Okay. So the question says, evaluate this 6xy ds, it's a big S, surface, over some surface S, where S is the portion of the plane x plus y plus z equals 1. So that's the plane which is defining our surface. That lies in the first octant. Okay. So this is a plane that by itself, this equation of this plane, of course, extends to infinity in all of the x, y, and z dimensions. But this says that lies in the first octant. The first octant is that part of xy space where x is greater than 0, equal to y is greater than or equal to 0, and so is z. So that's what the first octant is. Okay, so the first thing we want to do is we want to take this surface, want to take the equation for this surface, and we want to sketch it to make sure we're visualizing it correctly. Again, x, y, z. Now, in fact, I think we came across this surface earlier on in the course, but we'll go through how you would work out what this surface is if you haven't seen it before. You can see that this is just going to be a flat surface inclined at some angle, and in order to work out the intercept points on the x, y, and z axes, you just set each of the other 2 variables to 0 in turn. So then you see that, of course, this intercepts each of these axes here, when these are, so this is 1, 0, this is 0, 1, 0, 0, this is 0, 1, 0, and this is 0, 0, 1. And so you'll your surface is the plane which connects these 3 points. So if any of you are looking at the notes, you'll note that in the notes it says, and is in front of the YZ plane. Because in fact we've defined it's in the first octant, then in fact it doesn't make any difference, the fact that the question is trying to encourage you to consider projecting it onto the YZ plane. But of course you'll get, because this is a scalar surface integral, you'll get exactly the same value of the answer, just projecting onto the XY plane. So in fact that's what we're going to do. We're just going to project onto the XY plane. Okay, so what we want to do then is we want to work out, first of all, what is our function of x and y. So our function of x and y is z, and z equals 1 minus x minus y. So the function that we're going to be evaluating is 6xy, but we need our projection term. So our projection term is going to equal 1, it's going to equal the square root of 1 plus dg dx squared plus dg dy squared. So that's the term that tells you about the projection of this plane down onto the xy plane. Now we'll see that dg dx is minus 1 and dg dy is minus 1. So our projection term is going to equal the square root of 3. So the next thing we need to do then is work out what is the area, what is the region that we are projecting down to on the xy plane. So now we're going to recast our integral in terms of d, and d is our area on the xy plane. So we are integrating 6xy Okay, so we're integrating 6xy. We have our projection term, which is the square root of 3. We're going to integrate this with respect to dy and dx. And we need to work out what our limits are going to be when we project onto the xy plane. So our limits when we project onto the xy plane are going to be x goes between 0 and 1, and y goes between 0 and 1 minus x. So this is actually a region, this is a surface and a projection onto the xy plane, which we did earlier on in the course when we were playing around with integrals in multiple variables. So those are our regions of integration, and we integrate our 6xy dy dx with respect to that. We have our projection term, which we can put in front here, and we should, with a little bit of algebra, we should end up with the expression root 3 over 4. And that's the value of our scalar surface integral in this case. Okay, good. So next we're going to look at a scalar surface integral in the case that our surface is parameterized. So in this case we're going to return to our hemisphere, which is a shape that comes up very often in this course and also in many problems. It's a favourite shape. So we have, again, x, y, and z. So the question says then that S is the upper half of a sphere of radius 2. So this is this hemisphere. This radius equals 2. And we are meant to be evaluating over this surface S, Z, ds. Okay? Now, because we're doing a sphere, we're going to parameterize this surface in terms of spherical polar coordinates. So we know that the parameterization for this surface, and we did a very similar question yesterday, it's radius 2, so it's going to be sine theta cos phi I plus 2 sine theta sine phi j plus 2 cos theta k. So hopefully you've all got to the point by now that you've done enough examples of spherical polar coordinates that these just come out automatically. And again, to reiterate a somewhat tedious point, you really need to know what these are. You need to at least be able to visualize the geometry and work out what these are. These will not be given to you in an exam. Okay, so this is our parameterization for our surface. Because it's the upper half of a sphere, what's the ranges of our variables? So our polar angle then is going to go between plus pi by 2 and 0. And our azimuthal angle, as usual, goes between 0 and 2 pi. Well, in this case, we need to work out then, for our projection factor, we need to work out the derivatives of r with respect to our two variables. So you'll recall that when I was laying out the general formula for these things, I said we would take the cross product of r as a function of u and v. We take the cross product of r differentiated with respect to u with r differentiated with respect to v. In this case, u and v are phi and theta. So what we want to do is we want to take the derivative of r with respect to theta, and we want to take the derivative of r with respect to phi. And if we do that then, and we work out the magnitude of that cross product, so again there's some algebra here which I'm not going to do for you, you end up then that the magnitude equals 4 sine theta. Okay. So that then is your projection factor in this case. So our integral, it said that we want to integrate over our surface. We want to integrate z with respect to ds. So what is z in this parameterization? Z in this parameterization is the term in front of the k unit vector there. So z is 2 cos theta, or r cos theta. 2 in this case. So then our integral becomes integrating over our surface. This will now turn out to be, in terms of the variables theta and phi, we're going to be integrating 2 cos theta, which is z, times our projection term, which is 4 sine theta, and dA is going to be then in terms of phi and theta, where this is going to be theta between 0 and pi by 2, and this is going to be phi between 0 and 2 pi. You'll recall yesterday that when we were looking at the example of the vector area for a hemisphere, that again we had this was a very similar problem, and in that case, because we were doing it algebraically, we put in the term here r squared sine theta, which is the surface element in the spherical polar coordinate system, and you can see that this is, of course, the r squared sine theta term, because r is 2 from the square. Okay, so this is our integral. Our integral is 2 cos theta times 4 sine theta, integrated with respect to d phi and d theta. So there's no phi terms in there. There's not going to be any phi anywhere. So I can just take a 2 pi, which is what the integral with respect to phi is going to give us, and then I have here 8 cos theta sine theta integrated with respect to theta, theta between 0 and pi by 2. In order to solve this, I can use the double angle substitution, which tells me that 2 sine theta equals, sine 2 theta equals 2 sine theta cos theta. So I use this substitution. And when I do this then and put this all together, then I find that my surface integral in this case equals 8 pi. So those are 2 examples of scalar surface integrals. So they're the simpler flavour of surface integral, where you're already given the value of some scalar at the surface that you're integrating over. They're the less common type of surface integral that you encounter in physics, because most of the time in physics, so we'll see this more in the lectures next week when we're talking about the divergence and Gauss's law, most of the time what you're actually integrating, the reason you're doing a surface integral is because you're trying to understand what is the flow or the flux of some vector field through that surface. So it's normal, it's more common that you're doing vector surface integrals. So a well-known example of a vector surface integral then is Gauss's law, which in integral form says that the surface integral of the electric field through a surface is equal to the enclosed charge divided by epsilon naught. So it's important that you get some sense then of what these surface integrals of vector fields through surfaces mean. So in the illustration here, the magenta lines are indicating the electric field which is flowing away from some central point. And we are integrating, we're doing a surface integral of that over that surface. If you think of your vector field instead of, for example, describing the motions of some particles in a fluid, for example, the motions of particles in a liquid or in a gas, then this surface integral would actually tell you what the flux of particles was across that boundary. And more generally speaking, we use this expression flux just to describe the surface integral of some vector field through some surface. So something which we're going to encounter in a moment, which is obvious and we've mentioned a little bit previously, is that of course all surfaces have 2 normals. So if you like, in terms of a closed surface, there is an inwards and an outwards pointing normal. The convention, which is usually stated in questions, but not always, so the convention in the case that it's not stated, is that if the surface is closed, then you choose the normal vector which is pointing outwards. And the reason this is physically motivated, because as I say, what you're doing when you do one of these surface integrals in a vector field is you're trying to evaluate the amount of the flux of the vector field which is passing through that surface. Okay, so as I mentioned yesterday, there are basic rules for evaluating vector surface integrals. So if I'm integrating it again over some surface, I integrate the dot product of my vector field, which represents my flux, or which represents the flow of my fluid or my field. ds, remember, is n ds, where ds is the scalar area, and you will see these two terms used interchangeably, so you should always remember that's what they mean. This will equal the projection of this vector field onto some plane, typically the xy plane, where you now integrate the dot product of your vector field with the k minus I dg dx minus j dg dy with respect to dA, where this dA is typically dx dy. And as I mentioned yesterday, of course, the normalization of this normal vector, which would be underneath here, cancels with the projection term, and that's the projection term that we saw when we were actually looking at the scalar integral just then. And then similarly, that's the non-parametric case. In the parametric case, your vector surface integral is again given by your surface recast in terms of some parameters, which in this case will be du dv, and it's the dot product of your vector field with the cross product of two vectors which lie in the plane of the surface. So you should, at every point, really be able to look at a problem and work out which approach you're going to have to take. There's only really 4 different approaches, so you can memorize them, but you should be able to look at a problem and understand which approach you should take when tackling it. Okay. So this I've already said, this is on the board then. This is the expression that we worked out yesterday. Recall that we worked that out in 2 different ways. We worked it out both from the gradient of an equipotential of a 3D scalar field and by considering two vectors in the plane of the surface. And as I've said, the normalization cancels out exactly with the projection term, which is very convenient. And similarly, the same thing as I've just done on the board for the parameterized case. Okay, so let's do an example of a vector surface integral which is approaching the kind of level which you might get asked in an exam. So here we go. Here's a vector surface integral. So you're being asked to evaluate, and you're fortunate because you've already got the sketch on there, but we'll sketch it out badly anyway. So the question says evaluate the vector surface integral f dot ds. So the first thing you need to know is what's your vector field. So your vector field is yj minus zk. And S is the surface given by y equals x squared plus z squared. For the range, y goes between 1 and 0. And a disk described by x squared plus z squared is less than or equal to 1 at y equals 1. So that's fairly typical of the kind of description which you might get in a question, okay? So, when you got those words, and ignoring the fact that you've already got the nice sketch there, how would you work out what this is? So the first thing that we see is actually our surface is being defined by y as a function of x and z. So you could, if you like, you could rotate your coordinate system in your sketch if you feel more comfortable with your surface always being up. But we'll have our surface along the y-axis, just lying on its side here. What you immediately see then is that when you're doing your projection, we will not be projecting this time onto the xy plane, but we'll be projecting onto the xz plane. Okay, so that's just a little trick to try and catch people out. The shape of this paraboloid is, as the name suggests, a parabola on all sides. And it goes from y equals 0 to y equals 1. Okay? So that's a three-dimensional shape around like this. And it is capped at y equals 1 by a disk which is defined by x squared plus z squared is less than or equal to 1. So that essentially means that's obviously the equation of a circle, and that means that it's got all the ranges between 0 and 1. So that's essentially shorthand for a disk of radius 1 at y equals 1. Let's just check for a moment that, this disk is sealing this paraboloid shape. Okay, it's not necessarily the fact that the disk they've given you actually matches onto the paraboloid shape, but it's easy to do, of course, because the paraboloid ends at y equals 1, and our disk is defined at y equals 1. So we can just see what is the shape of our paraboloid surface at y equals 1. And if I took y equals 1 into there, I get 1 equals x squared plus z squared, which is, of course, exactly the outer boundary of the paraboloid at that point. So we have a completely sealed shape, which is a paraboloid going from the origin to y equals 1, and then it's sealed by a cap at y equals 1. Now, these two shapes are defined completely differently, so we will need to do our surface integral by separating it into two parts. We will need to do a surface integral over the paraboloid shape and also a surface integral over the cap at the end. Okay, so normally we would say that we had a g of x and y, and then we'd say that we had an f. So normally we'd say we describe our surface as g of x and y, and then we would say that we had some f of x, y, and g of x and y. And that's fine, that's the approach we're going to take. But in this case, actually, of course, our g, our surface, is a function of x and z. That's our parabola. And that equals y. So this equals whatever it was, x squared plus z. So we want to work out what is the gradient of some 3D scalar field, which is the equipotential of this. So if we have some x of x, y, z, this equals y minus x squared minus z squared. And then we want to take the gradient of this 3D scalar field, which is going to give us a normal to this surface, just as we were discussing in previous lectures. So we take the gradient of this. So the gradient of this is k minus 2xi minus 2zk. Not. Sorry. Right. So if we look now at that vector j minus 2xi minus 2zk, so it goes in the positive. If I imagine now I have some point on my surface, it goes in the positive j direction, it goes in the negative x direction. So I think I couldn't really tell from that whether it was pointing inwards or outwards, but it also goes in the negative z direction. And if you if you think about this for a second, if you work out the consequent vector, you will see that the normal we have calculated here is actually pointing inwards. So what we need to do is we need to flip the sign of each of the terms of our vector to make it point outwards. So we end up with our normal being 2xi minus j plus 2zk. And as you know that the normalization of this we don't really care about, the answer is 3, but we don't really care about it. It's just going to cancel with the projection term, so we're not going to worry about evaluating it. Alright, so what we want to do now is we want to work out the dot product of our normal with our vector field. So the dot product of our normal with our vector field. So our vector field is given by yj minus zk. And we're dotting that with 2xi minus j plus 2zk. So we end up here with minus y minus 2z squared. And we substitute in for y equals x squared plus z squared, because we want to be projecting this onto the xz plane. So we want the thing that we're integrating to be in terms of x and z. So then that equals minus x squared plus z squared minus 2z squared, which equals minus x squared minus 3z squared. Okay, great. So this is the function which we need to evaluate projected back onto the xz plane. However, sketch it again. Here is our shape, and this is our surface projected back onto the xz plane. So if I project this surface back onto the xz plane and see what shape it describes, then I find very badly that the projection of this surface onto the xz plane is a circle of radius 1. Now, of course, we can evaluate this in terms of x and z coordinates, but it's much easier to switch it to plane polar coordinates. Okay, so we will make our plane polar coordinate substitutions. So we say that x equals r cos theta. Z, in this case, is taking the place of y. So z is r sine theta. If we substitute then in, we get that our integral becomes theta goes between 0 and 2 pi, r goes between 0 and 1, r squared cos squared theta plus 3r squared sine squared theta, all with respect to theta and r. But then, of course, we've switched our variables from plane Cartesian to plane polar coordinates, so we need to add in our old friend the Jacobian here. And then you can make a couple of standard substitutions. You make the substitutions of cos squared theta equals a half cos 2 theta minus 1, and sine squared theta equals a half 1 minus cos 2 theta. And if you make those substitutions, then you end up with an integral which you can solve. This comes over here. And you end up that the vector surface integral for the paraboloid is minus pi. Okay? So that is the numerical value of the flux of that vector field through that surface. All right. But we also need to add on to this the vector surface integral, which is associated with the cap, the shape on the end of the paraboloid. So how do we do that? So for this shape on the end of the paraboloid, for this cap on the end of the paraboloid here, then we can immediately see that the normal to this surface is simply going to be j. It's going to be the unit vector in the y direction. So our integral, and we can also see that, of course, this projects a surface, this projects a circle of radius 1 down onto the xy plane, just as the paraboloid did. And that's not a surprise because the two surfaces touch and they match. So our integral becomes the integral of the dot product, which in this case, our vector field is yj minus zk. We dot it with our normal, which is just j in this case, which means that we are just integrating over dy. Y equals 1, right? Because our cap only exists at the coordinate y equals 1. So this means that we are doing a double integral of 1 over the projected area of a circle. When you're integrating 1 in 2 dimensions, you're just calculating the area. Just as you'll recall way back a few lectures ago, we did the example of where you're integrating 1 in a triple integral just gives you the volume. Okay. So integrating 1 for this 2-dimensional just gives you the area of the circle. So you can work it through and calculate it, or you can just immediately see intuitively that this is going to give you the area of a circle of radius 1, which is pi 1 squared, which is pi. So that's the value of the flux of this vector field through the cap. And then we see that our total value of our integral is equal to, rather frustratingly, is equal to minus pi plus pi, which is 0. So that's the mathematical answer, and then you might want to think about what does this mean in terms of the physics of the question being asked. What this means is that the net flux of this vector field, of the vector field described by whatever the expression was, yj minus zk, through this surface is actually 0. This means that the net amount of this field flowing in and out of into this surface or out of this surface is 0. Just as much is flowing in as is flowing out. So let's see if we can zip through one final example. So then the final example, which we'll try and zip through then, is evaluate a vector surface integral in a parameterized sense. So again, it's our old friend, the upwards pointing hemisphere. Evaluate the vector surface integral where the field, so you should always imagine when you visualize these things, what we do is we always just sketch the surface. But you should imagine there's the vector field there in the background flowing through or in some complex way through this surface, because that's what you're evaluating. All right. So we want to integrate f dot ds, where f is given by xi plus yj plus z to the fourth k, over over the upper half of the sphere given by x squared plus y squared plus z squared equals 9, i.e. it's the upper half, it's the upper hemisphere of a sphere of radius 3. So I'll just shortcut you through the steps, which are also in the notes then. So the first thing we need to do is we need to work out our parametric expression. Our parametric expression is going to be r sine theta cos phi I plus r sine theta sine phi j plus r cos theta k, as ever for a sphere. R is equal to 3, and our limits are the same as they've been in the previous examples where we've done upwards facing hemispheres. So theta is going to go between 0 and plus pi by 2, and phi is going to go between 0 and 2 pi. We evaluate dr d theta and dr d phi, and we work out the cross product of these two. There's a few lines of algebra in here, but we work out that the cross product is given by minus 9 sine squared cos phi I minus 9 sine squared sine phi j minus 9 sine theta cos theta k. And again, in this question, if you look at that cross product, which is a normal to the surface, you will see that that is pointing inwards, and the question specifically says that the vector field is pointing out of the sphere. So we take the reverse, we take the negative of this in order to take a normal which is pointing outwards from the sphere. Okay? So we take all of these terms and we choose this normal. What we do then, the final steps are we take f and we convert it to spherical polars. And we end up with an integral which looks like this. It's in the notes. So our integral ends up being phi between 0 and 2 pi theta between 0 and pi by 2 of 27 sine cubed theta plus 729, nice easy one, sine theta cos to the 5th theta d theta d phi. And there is some algebra, and actually it's not quite as bad as it seems, and you end up with an answer of 729 pi for this particular vector surface integral. Okay, so we're pretty much done. So I appreciate that was there was not a lot of new concepts in that lecture, but it's important to understand the steps that you need to go through in order to be able to evaluate these surface integrals, because they really are a key part of the kind of questions that you're going to get. In the lectures next week, we will look at the final two of the triumvirate of div, grad and curl. So you'll be learning about divergence and curl next week, and I'll see you then. Bye.